All right, let's talk about something really on the cutting edge, the intersection of AI and quantum computing. We're going to cut through all the hype, figure out where this tech really stands today, and we're going to uncover a pretty amazing breakthrough that could seriously change modern medicine.
So to set the stage, let's start with a number. $3 billion. That is the estimated price tag to bring one single new drug to the market. It's a staggering cost and a huge barrier to developing new treatments.
And it's not just the money, it's also the time. On average, it takes a full decade of research, development, and trials. And even after all that, the success rate is only about 10%. It's an incredibly long, expensive, and risky gamble.
So you've got this massive $3 billion, 10-year problem. So the big question is, could a totally new kind of computer be the answer? People are betting that this fusion of quantum computing and AI could be a game changer, but to see why, we first have to understand how AI even thinks in the first place.
Right. Before we can even touch the quantum stuff, we need a quick look at how the powerful AI models we have today learn to see patterns, especially when they're looking at images.
So what you're looking at here is a classical AI model. It's called a convolutional neural network, or CNN for short, and you can kind of think of it like an assembly line for vision. The first part of the line, called feature extraction, just breaks an image down into its most basic parts. It starts by seeing simple lines and curves, and then it combines those into more complex shapes and textures. Then, the second part, classification, takes a look at all those features it found and makes a call. Okay, based on these particular shapes and textures, I'm 99% sure that's a picture of a dog. It's an incredibly powerful system, but it's all built on simple, classical computer bits.
Okay, now here's where things get really interesting. We're going to take those simple, classical bits we just talked about and swap them out for something, well, something a whole lot weirder. It's time to bring the strange, powerful rules of quantum mechanics into the picture.
And here it is, the fundamental difference. A classical bit? That's just a light switch. It's either on or it's off, a 1 or a 0. Dead simple. But a quantum bit, a qubit, is a whole different beast. It's more like a dimmer switch. Thanks to this wild property called superposition, it can be a 1, a 0, or it can exist in this kind of blended state of both at the exact same time. And that opens up a ridiculously huge new space for doing calculations.
This sphere, this really helps you see that power. A classical bit can only be at the two poles, right? The very top for a 0 or the very bottom for a 1. But a single qubit can exist at any point on the entire surface of this sphere. That massive, massive increase in the amount of information one qubit can hold is where all the theoretical power of quantum computing comes from.
So, what happens when you take that AI assembly line we talked about and you power it with these supercharged new qubits? Well, you get a quantum convolutional neural network, or a QCNN. The whole idea is to use these quantum properties to spot patterns that are just way too complex for any classical computer to even dream of handling. In theory, it should be a massive upgrade. But what actually happens in reality?
I mean, the theory sounds incredible, right? But when researchers actually built one of these QCNNs and put it head-to-head with a classical one on a pretty standard task, they ran smack into a surprising reality check.
Yeah, the results were not what you'd think. On a simple image recognition test, the good old classical AI was basically perfect, and the powerful, new quantum AI, it was barely better than a coin flip. A total bust. So what on earth went wrong?
Well, the answer is all about the era we're in right now. It's called the NISQ era, which stands for Noisy Intermediate Scale Quantum. And you can think of today's quantum computers as these incredibly powerful but super fragile prototypes. They just don't have that many qubits yet, they get easily messed up by noise from, well, literally anything in their environment, and they can't hold on to their special quantum state for very long. See, high-accuracy AI needs really deep, complex calculations, and today's noisy hardware, it just can't run them without the whole thing basically falling apart.
So, does this mean quantum computers are just a bunch of overhyped nonsense? Absolutely not. It just means we've been asking them to do the wrong job. See, instead of trying to beat classical computers at a game they're already great at, we need to find problems that are uniquely suited to the way quantum computers think.
And this case study is the perfect example of that shift in thinking. Instead of a task like image recognition, which classical computers are great at, researchers focused on something they really struggle with, accurately simulating a complex molecule like collagen to predict if it's toxic. They used a special quantum algorithm designed to find the molecule's lowest energy state, basically its most stable form. And the quantum computer's prediction? That this molecule was stable and had low toxicity. And here's the best part. That prediction was a perfect match with real-world lab data. And this is exactly why it worked. Simulating the quantum behavior of molecules is what quantum computers were literally built for. They're at home with all the complex interactions and quantum effects that classical computers can only guess at. They are the right tool for this very specific and very important job. So, what does this all tell us about the future of quantum AI? Well, it shows that progress isn't going to be one giant quantum leap. It's going to be about taking smart, strategic steps forward. The key takeaway for researchers right now is this trade-off. You can design a really deep, complex quantum model that, in theory, would be super accurate, but it just won't run on today's noisy hardware. Or you can design a shallower, simpler model that is compatible with our current NISQ devices, and you can get some really solid, though not perfect, results. All the real, practical innovation is happening in that second bar.
And that really leaves us with a final thought here. The most important question isn't, when are quantum computers finally going to be perfect and powerful? It's what are the right, high-impact problems we can solve with the imperfect ones we have right now. The real excitement isn't about waiting for some distant future. It's about cleverly matching the unique abilities of today's quantum computers to our biggest challenges, like finding that next life-saving drug. It's about being smart with the tools we have today.